2.4, partition matrices. Just as we can partition a matrix into column vectors, we can also partition a matrix into blocks using horizontal and vertical dividers. Example 1, write A as a 2x3 partitioned or block matrix. So here, they gave us the partitions already. So we're going to have A equaling. So this block here would be A11. Okay, this block here would be A12, and the last block would be A13 for row 1, column, whatever it is. The block down here, -8, -6, 3, would be A21 because it's row 2, column 1, A22 for 1, 7 because it's row 2, column 2, and A23 for -4. And I'm just, for the sake of this example, for when you're going back, A11 you would say is 3, -5, 0, 2, -1, 4. A12 would be 5, 0, 9, -3. And A13 would be -2, 1. A21 would be matrix -8, -6, 3. A22 would be matrix 1, 7. And A23 would be matrix -4. Addition and scalar multiplication of partition matrices. If matrices A and B are the same size and partitioned in exactly the same way, then each block A plus B is the sum of the corresponding blocks of A and B. Scalar multiplication is also computed block by block. Partition matrices can be multiplied by the usual row-column rule, as if the block entries were scalars, provided that for a product AB, the column of A matches the row partition of B. A and B are conformable for block multiplication. Let's go ahead and look at example 2. We're going to let A be this partition matrix, with this being block 1, 1, block 1, 2, block 2, 1, block 2, 2. And B is this partition matrix with blocks B1 and B2 here. We're going to compute AB by multiplying the blocks. So the first thing I would do is we're going to write this out, our AB, out as our blocked matrices. So A11, A21, A12, A22, my blocks, times B1, B2. And I'm going to do the multiplication here to get my matrix. So when I multiply this through, it'd be A11 times B1 plus A12 times B2. And then I would have A21 times B1 plus A22 times B2. And that's going to give me some answer here. And what I'm going to do is I'm going to find this first multiplication here, then this one, add them together. And that would become my top block here. And then do this matrix multiplication and this matrix multiplication, add them together, and it would be my block that comes down here. So let's start with A11 times B1. So A11 would be 2, 1, -3, 5, 1, -2. Times B1, which is 6, -2, -3, 4, 1, 7. When I go ahead and I multiply those through, I get 15, 2, 12, -5. A 2 by 2 matrix. Now we're going to go ahead and find A12 times B2. So that would be 0, -4, 3, -1, times -1, 5, 3, 2. When I multiply that through, I end up getting negative 20, negative 8, negative 8, 7. Then when I take these and add them together, that is going to be this block up here. So I take these, add them together, and I get negative 5, negative 6, 4, 2. So that would be the top part here. Okay. Now what we need to do is we need to find A21 times B1. So A21 is 0, negative 4, negative 2 times B1, which is 6, negative 2, negative 3, 4, 1, 7. When I multiply these together, I get 14, negative 18. Then I need to go ahead and find A22 times B2. A22 is 7, negative 1 times B2, which is negative 1, 5, 3, 2. And when I multiply these, I get negative 12, 19, I believe. Then I go ahead and I add these together, and I get 2, 1. And that would go right here. And these would be your 2 blocks. So your final answer would be this. By taking this work together, we added these two together, and we added these two together. Example 3, let A be negative 3, 1, 1, negative 4, 2, 5, and B be A, C, E, B, D, F. Verify that AB equals column 1A, row 1B, plus column 2A, row 2B, plus column 3A, row 3B. Okay, so we need to go through and verify all of this. So the first thing we're going to do is column 1A, row B. So negative 3, 1 times, row 1B, AB. And when I multiply through, I get negative 3A, negative 3B, B. Next, we're going to go ahead and do column 2A, row 2B. So it would be 1, negative 4 times CD, and I end up getting C, negative 4C, D, negative 4D. And then I'm going to find column 3A times row 3B. So this would be 2, 5 times EF. And I'd end up getting 2E, 5E, 2F, 5F. And then I need to go ahead and add all of these together. And I would get negative 3a plus c plus 2e, a minus 4c plus 5e, negative 3b plus d plus 2f, and b minus 4d plus 5f. And that's just verifying all the row operations that we did to find it. Multiplying matrices. 1. A times vector x equals a1 times x1 plus a2 times x2 all the way to ap times xp. 2, a times b is a times b1 all the way to a times bn. 3, the row column rule. 4, entries in AB are rows of A times B. And then our next theorem, which is theorem 10. Theorem 10 states it's column row expansion of AB. If A is an n by n matrix and B is an n by p matrix, then you can go through and multiply the columns of A by the rows of B, and you would go through and get your answers. And we're going to demonstrate that on the next example as well. Let's look at example 4. We have matrix A equaling A11, 0, A12, A22. We need to find a formula for A inverse. So we're going to have a formula for this. So the first thing we're going to do is we're going to make some assumptions. So first, A11 is a P by P matrix. A22 is a Q by Q matrix. A12 is a P by Q matrix, and A21 is a Q by P matrix. Also, we're going to assume A is invertible. And we're going to let B equal A inverse. So let's go ahead and set this up. So I have my matrix A11, 0, A12, A22 times matrix B. So I have B11, B21, B12, B22. And this equals my identity matrix IP, IQ. So we're first going to come up with our formulas for each one when we do our row column multiplication and what it equals. So the first one I would have AII or A11 times B11 plus A12 times B21, and that would equal my identity matrix P. Then I would have A11 times B12 plus A12 times B22, and that would equal 0. Then the next one, I would just have A22 times B21, and that equals 0. Because of this 0 here, I lose out on a term. And the same thing with the next one, I would have A22 times B22 would equal my Q identity matrix. And so we need to come up with a formula for each one of these because we're letting matrix B equal A inverse. So the first thing I notice here, I can eliminate, because I have the identity matrix here, I can eliminate A22 by taking the inverse. So A22 inverse, and I end up getting B22 equals A22 inverse by the invertible matrix theorem. So that's the first thing I can do. So I've established this. So then I can go, and since I have B22 equaling A inverse, I look up here, A22 inverse. I can have B21 equal, like if I took the inverse of this one, since I have it, B21 would just be 0. Okay, so looking at this one here, I would have B21 equaling A22 inverse times 0 to get rid of this A22, which equals 0. So that would be my second one. Now, A11 and B11 equals the identity matrix for P. Therefore, A11 is invertible by the intermediate, by IMT, the invertible matrix theorem. So another thing that I have is A11 times B11 equals the identity matrix P. Therefore, A11 is invertible by the invertible matrix theorem. So I have B11 equaling A11 inverse. So I have, so far, I have B22, I have B21, and I have B11. So the last one I need to find is B12. And with B12 is in this one here. So I would go ahead and solve for B12 using your order of operations for this one. So for that last one, I have A11, B12 plus A12, A22 inverse would equal 0. And then this would be A11, B12 equaling negative A12, A22 inverse. And then I would go ahead and take the inverse of A11. So B12 would equal negative A11 inverse, A12, A22 inverse. So my formula for A inverse which equals B. So we'll put those all in there. If you look up here, this was B. So we'd start with B11. B11 we said was A11 inverse. And then B21 we said was A22 inverse, which actually B21 0. Which ends up being 0. And then B12 we just got right here, which is negative A11 inverse, A12 times A22 inverse, and then B22 we said was A22 inverse. And that would be your formula for these. Block diagonal matrix. A partition matrix with 0 blocks off the main diagonal of blocks The theorem being a block diagonal matrix is invertible if and only if each block on the diagonal is invertible. Show that IA01 is invertible and find its inverse. So IA0I, its inverse would just be I negative A 0I. Switch these, negative these, and it's just multiplied by 1. In example 6, compute X transpose X when X is a partition matrix as X1, X2. So let's start with X transpose. That would be X1, X2 transpose, which equals X1 transpose X2 transpose. So X transpose X would be X1 transpose X2 transpose times X1, X2, which would then equal, using your row column multiplication, X1 transpose X1, X2 transpose X1, X1 transpose X2, X2 transpose X2. And that would be your answer.